Good morning, Professor Nomura.
Good morning.
Good morning. Thanks for chairing the session this morning.
Yeah.
Good morning, Professor Tanaka.
Hi, good morning.
Good morning. Please, I have passed the host access back to you.
Okay, thank you. Noted.
おはようございます、羽生先生。
おはようございます。すみません、ギリギリになっちゃって。
よろしくお願いします。
はい。予定通り10時からでいいんですよね。
そうですね。はい。
はい。
野村先生、よろしくお願いします。
はい。
ありがとうございます。
よろしくお願いします。
よろしくお願いします。野村です。阪大の。
なんか全然すみません、ちょっと会議の週でこれほとんど参加できなくて、今日午前中は聞こうっていうかな参加できるぐらいで、本当に申し訳ない。
昨日深見先生に講演していただいて、はい、私も終わって、野村先生も終わって。
そうですか。やっぱり現地に行かないとダメですね、みんな。皆さん、なんか内職しちゃって、現地行ってればみんなちゃんと。
1週間シンガポールに行ってたいなと思ったんですけど。
そうですよね。そっちの方が本当、ちゃんと。
またトライしましょう。
はい、ぜひ。よ
ろしくお願いします。
大学にいるとダメなの。仕事できない。
総勢160人以上登録してるみたいなので。
素晴らしいです。
見かけの人数少ないんですけども、YouTube 側で見てる人が結構いる。
はい。じゃあ。
シンガポールの Zoom の、コントラクトの人数の制限があるらしくて、見かけ上は少なく見えるんですけど。
いろんなツールができて、そういう意味ではいいですね、そういう意味
で。いいんですけど、現地行ってマーライオンにお目にかかる。
これなんかビッグパマ。
はい。
なんか、
インスパイアードコンピューティング。
だから、なんかビッグパパにすればいいんですかね、それで。なんか、うまく。
ビッグパパだとなんかね、別な登録商標みたいなのあるらしいです。
なるほど。
ビッグパパだと。
そうですか。ビッグパパとかビッグママとかにすればなんか
違う意味になってインターネットで出てきます。
A407, please use your real name.
Oh, yep. Real name. Huh? Not Big Papa. So, Prem, you can read Japanese characters.
I can read only hiragana and katakana. I mean, long ago.
Wonderful.
Even that I don't remember now much.
Yeah. So you were in Matsumoto, right? Long years ago.
Yes, yeah. In Nagano City. Yeah.
Yeah, it's a beautiful place.
Yeah, yeah. The person with A407, can you identify you either by showing your face or use your real name? If not, we will remove you.
Are you talking to me?
No, there is one person with A407.
A47. I'm not sure.
Saprit, if there is no response, please.
Yeah, I'm trying. Sorry.
Where are you from?
Cannot change the name. So.
Okay, it's okay. As long as you are a proper attendee. Then
Who are you from Tohoku University? I will go into the, I think, to the, okay.
Okay, no problem. No problem.
Okay.
I mean, the first day we had some problem with intruders. Yeah, so we just wanted to make sure that all are genuine attendees. No problem.
It's a Professor A47.
Yeah, it's fine. You can keep it as it is.
Maybe I will once go out and.
That's a Horio Sensei.
Hi, domo. ちょっと入りましょう。
Oh, okay, then it's fine. Yeah.
That's fine. We can translate.
Thank you.
So may I share my slide? A little bit earlier.
But I think it's okay. So yes, please.
Okay, thank you. Because I'd like to check my slide condition. It's okay?
Yeah, perfect. Okay, it's time. So I'd like to start this session. I'm chair of this session. I'm Hikaru Nomura from Osaka University. And today, good morning, everyone. Today, we have a 3 talk in the morning session. And the first talk is by Professor Hanyu from Tohoku University. And the presentation title is Challenge of MTJ-based non-volatile logic in memory circuit and their applications. So please start your presentation.
Thank you, Professor Nomura. Good morning, everybody. Can you hear me? It's okay? Okay. So I'm Takehiro Hanyu from Tohoku University, Japan. The title of my talk is Challenge of MTJ-based non-volatile logic in memory circuits and their applications. The contributors of this work are the Mr. Takahiro Oka, the Dr. Daisuke Suzuki, and Dr. Masanori Natsui. And part of this work was supported by JSPS Kakenhi, JST Crest, JST Opera, and the industry academic collaboration of SHEETS Consortium. Okay, so first of all, let me start from the background of this work. As you know, the artificial intelligence AI has potential advantage in social applications such as security for home automation, factory automation, and the internet communication, and infrastructures and energy harvesting control, medical healthcare diagnosis, and agricultural plantation, building maintenance, electric vehicle, and so on. And Internet of Things, IoT, has been also spreading wide range of applications. So the AIoT is a judicious combination of AI and IoT. So what is the Society 5.0? It is defined as the human-centric society that advances economic advancement with resolution of social problems by a system that highly integrates cyberspace and physical space. Society 5.0 was proposed in Fifth Science and Technology Basic Plan as a future society that Japan should aspire to. It follows the Hunting Society, Society 1.0, the Agricultural Society, Society 2.0, Industrial Society, Society 3.0, and the Information Society, Society 4.0 at present. Okay, so what could be achieved in Society 5.0? At present, Society 4.0, the knowledge and information are not shared, and the cross-sector value is difficult to create. But in Society 5.0, the IoT will connect all people and things. The all sort of knowledge and information will be shared, and totally new value will be born. And a variety of constraints exist with respect to social problems, such as the aging society and regional depopulation, making sufficient response difficult. In Society 5.0, the social issues will be overcome, and humans will liberated from the various types of constraints. And information complexity is also overcome in the Society 5.0. AI will free humans from the burdensome work of the analyzing the huge amount of the information. And of course, the robot technique is very helpful for the humans in the Society 5.0. In this way, it's a very attractive future in the Society 5.0. So what is the key technology to open the door of the Society 5.0 world? We have pointed out three keywords. One is improvement of AI processing capabilities. The method to improve the performance in the AI processing is connectivity. It's very important. Connectivity between logic and memory modules. To realize this connectivity improvement is the architecture revolution is necessary. The logic memory architecture is very attractive keyword to realize these kinds of the high performance AI processing. And the second issues is power reduction. this ultra low power dissipation is necessary in the IoT application. To realize these kinds of ultra low power dissipation, the power getting is a very useful method. To realize the power getting, non-volatility is very important. And the third keyword is the compatibility of silicon integration. At present, electronics devices, the elements are succeeded by the silicon technologies. So this compatibility of silicon technology is very important to realize the new hardware world. So fortunately, the MTJ is very compatible with the silicon technology. MTJ is just stacked on the MOS transistors. So today's my presentation title is the challenge of MTJ-based non-volatile logic memory circuit and the application. We include these three keywords in my presentation. Okay, this slide shows the symposium VLSI, the held in this year, June. This is short course slide, and Dr. Chai is present at TSMC. He just pointed out these kind of three keywords: the logic density, memory density, and the connectivity. These three kinds is very important. The system level performance requires the balance among logic, memory, and connectivity. This connectivity is important in the system level performance improvement. And this is also the Symposium of VLSI Technologies short course slide. The Dr. Lu-san is Matronics is present in this kind of presentation. Left-hand side is the conventional von Neumann architecture. The right-hand side is the new architectures. In von Neumann architectures, there are several words, the memory words. The A is limited is SRAM density and the bandwidth limitation of the data movement, and also the power consumption problems. They happen in these kinds of non-volatile architecture. In contrast, if you use the computer in memory or functional memory architectures, it's very to compute the data inside memory with much less data movements, and the memory rich and the logic this balance is very important. Anyway, this CMOI, computer in memory, the in-memory architecture is very useful to realize these kinds of system level performance improvement. So I'd like to explain the non-volatile VLSI. So the slide left-hand side is the conventional architecture. This is von Neumann architecture. In von Neumann architecture, the logic and memory modules are separated and many interconnections between modules. So the wire delay dominates the chip performance, and the global wire requires large drivers. Then the on-chip memory is also volatile. The power supply must be continuously applied. Then the delay becomes long and the static power becomes high. So if you use the logic in memory architectures, we use these kind of the MTJ device. MTJ is a magnetic tunnel junction device. It's okay. This is very attractive. There are several attractive features. Of course, this is non-volatile device, and the unlimited endurance, the high speed, writability, and the scalability, CMOS compatibility, and the three-dimensional stack capabilities. So the storage is non-volatile. The MTJ devices are put on just CMOS layers, and the storage and logic element are merged. So delay becomes short, and the static power can be greatly reduced by using these architectures. okay, so help to remove the wasted standby power. The left-hand side is the conventional volatile memory-based architecture. In the volatile, this is Islam-based. This is volatile memory architectures. It consumes the static power. This blue color is the static power. This red one is the dynamic powers. The power is always turned on, then the static power consumes. But if you use the non-volatile storage element, we can remove this idle, between the idle state, we can remove the power supply. So this power switch is quickly turn on and off, then we can remove the wasted power. So the great reduction of the power dissipation is possible by using the power gettings combined with non-volatile device. And there are several non-volatile memory devices, but we just focus on the this kind of Spintronics device. This MTJ also the Spintronics device. It has a very good score. You know the flash memory. You know they're commercially available and a very useful device. But okay, very good thing is non-destructibility and the scalability is wonderful. But several problems happen by using the working memory. Okay, this is all the storage memory. It's okay, but if you wanted to use this device as a working memory, is not so good. How about the FE-RAMs? So it's not so perfectly not comfortable. Then this the Spintronic device MTJ is very wonderful score. So we use this device as a working memory in the computer system. We have already successfully designed to fabricate this kind of the VSI components. This is the logic component. This is general purpose component, and FPGA also the fabricated, and TCAM. So this is the functional memories also fabricated, and we can check the performance. And this is non-volatile SRAM is also fabricated, and this is a microprocessor unit, and this is microcontroller unit. Okay, this is first version. In the second version, this is 2 years ago that we have successfully fabricated and presented in the ISCC and something. And last year we have our new SOT MTJ based. The MRAM is also fabricated and presented in the VLSI symposium. This way, this kind of fabrication is possible, and this kind of the very huge size of chip is also fabricated by using these techniques. But we must consider the drawbacks and also consider its solutions in MTJ-based non-volatile logic memory LSIs. Drawback one, this is a large light energy in MTJ. So if you would like to use these kind of non-volatile logic memory LSIs, the conventional CMOS circuit cannot simply replace to non-volatile logic circuit. For example, the data shifting is there. Many writing is happen. So my first presentation is we will propose a new non-volatile oriented data shifting technique. This is the first topics in my presentation. And the second topic is decrease error tolerance in MTJ CMOS hybrid circuit. This is silicon error size also must be considered this kind of the error tolerance. But okay, in this integrated circuit is MTJ, the most transistor is hybrid structure. Then it happen the same die, so this kind of the error tolerance is happen. So in our present propose, we propose the error tolerant technique using the MTJ device. Okay, so I'd like to explain the non-volatile oriented data shifting and its application. The first topics. Okay, this figure shows the FPGA. The FPGA is the mapping in the lookup table to these kind of the circuit configurations. So the FPGA looks like logic component, but actually almost the memory device. So many large capacitor the memory storage element is stored in the FPGAs. So, but very flexible. It's very attractive features, but the standby power is problems. And the first drawbacks, how to realize data shift. FPGA component has realized these kinds of the data shift. Data shift is realized by the SRAM cell. This is connection of the SRAM cells. So if you simply replace this SRAM cell to the non-volatile one, so many data write operation is necessary. For example, if the input is 6-bit input, so this SRAM cell is 64 SRAM cell is necessary, is needed. So the 1-bit shift operation needs 64 times writing is necessary. If you just simply replace the SRAM cell to the non-volatile one, that's the problem, because writing current is increased, is very large compared with the silicon-based realization. It's about 5 times or almost less than 10 times larger than the SRAM silicon-based realization. That's the problems. So we must consider this problem. Okay, our approach is just a very simple one. 1-bit shift is just only 1-bit replacement. So we don't shift every bit. We just replace the only 1-bit. And this shift information is put on the control circuit part. Then we can greatly reduce writing, the number of writing cycles. So this is the very good. This is our idea to solve these problems. And we can check the realization performance. The first one is a transistor count. This is a conventional SRAM-based, volatile-based FPGA realization. And the middle one, second one is just simply replacement. The SRAM cell is just simply replaced to the non-volatile one. So its area is a little bit larger than the CMOS realization. But this third one, right-hand side is our proposed method. You can see the selector part is also reduced, and the memory area, number of transistors is reduced. And of course, this current controller part, this is new part because we are changes the circuit structures. But this overhead is very small. Then the total number of transistors is greatly reduced by using our approach. This is compared to the transistor count. And this is a comparison of the power dissipations. Okay, this left-hand side is a conventional SRAM-based realization. This input specification is this kind of processing. 8-bit shift is done and one cycle 200 microsec. This is time interval is like that time. Then, SRAM-based realization it consumes almost all the standby power is consumed because 8-bit shift is after that is just stopped. But this period is very difficult to power getting, but it consumes large standby powers. The second bar is the non-volatile SRAM-based realization. This is the lighting is so the same architecture. So the many lighting power is necessary. So it consumes very large power dissipation. The third bar is the only one light. This one is only final cycle is lighting. This is usually used this kind of method. But our proposed method is great reduction in power dissipation is achieved like that. So it's very useful for the reduce the power dissipation in our method. And this shift operation is very useful in the the neural network architectures. This is binary convolution neural network architectures. We can skip the details about, but this realization we have many data shift operation is used in these architectures. And this is layout design result, and this is the designed verifications, and this is also the verification by using the FPGA board. There we can get this the correct operation, and this is a comparison of the energies. You can see the our proposed method is great reduction is successfully done as shown in this figure. So in this way, this kind of the non-volatile based MTJ based non-volatile VSA is a very attractive features by using these kinds of techniques. And I would like to move on to the second topics. So design of an error-tolerant bit counting circuit in BCNN architectures. So this is error tolerance is very important to the method for the these kinds of applications. Okay, so our target network structure, this is the ReNet, and which is a typical DNN structure for the character recognition. In this network structure, which extraction is performed by alternating the convolution and the pooling and with classification performed in the full connection layers. Convolution operation, which account for the large percentage of processing. They consist of MAC operation. Because these operations are performed on the 5x5 map, accumulating 25 value is an important operation for this network structure. In binarized neural network, the multiplication and accumulation are replaced to the X norm and the bit counting respectively. Okay. And now I will explain the principle of the binarization. As I mentioned briefly before, the binarization enables the reduction of the memory and computational cost and the neural networks are binarized. Binarization are called binarized neural network. In these networks, it's possible to replace multiplication and accumulation with an XNOR operation and majority decision, respectively. There are four possibilities in signed binary multiplication, but by representing -1 with 0, and we can implement it with just XNOR operations. Since products are binary value as well, we can replace the summation and the threshold operation with majority decision. You may be concerned about the loss of accuracy of when performing binarization, but the previous research has demonstrated the effectiveness of BNNs. This figure shows the design of the XNOR gate based on the non-volatile logic in memory architecture. By the use of non-volatile logic in memory architecture, the stored data M is embedded into the logic circuit shown in these figures. Therefore, the circuit realization becomes compact. The differential pair circuit style is used where the current level 1, current level I1 is compared to the I2. Since the magnitude relationship between I1 and I2 represent the truth table of 2-bit XNOR function of the input value in and the stored data M shown in this table. This schematic of the one Mac operation using the conventional design. First, this structure performs bit width XNOR operation between the input and the weights. Then these results are accumulated using the adder tree. Finally, the output is determined by the comparator, which evaluates the accumulated result against the threshold. In these operations, we call the part of the bit counting operation, excluding the XOR. In the conventional structure, the bit counting hardware becomes large with the high power consumption. Now, let's explain the proposed compact and low power bit counting circuit. In sub I is the input value and the output is output value. Out is output values. The clock is CK, okay, CLK. Unlike the conventional structure, there are no adder tree and or comparator instead. The operations are integrated into one circuit that uses the multiple valued current mode linear summation. This circuit is roughly divided into two parts: sense amplifier part, and the the bit counting part, as shown in this figure. Okay, also I explained the operation of the bit counting unit. If the value and their complements are sent to the gate of each transistor connected to the connected in parallel, and when the value is 1, the current flow through the transistors. These currents are then the summed in the left and right parallel structures, respectively. That is this unit convert that the number of inputs that have logic level 1 into the current strength. Here we can consider the equivalent circuit of these parallel connected transistors as one variable resistance, as shown in these figures. For example, let's assume that more than half of the input value is 1. There's the current through the left side is larger than the current through the right hand side, and the equivalently the left hand side resistance is lower than the right hand side resistance. Let's add on the resistance and M and N at the number of the logic level 1 by input and complements, respectively. If the resistance of left hand and right hand side parallel transistors are R1 and R2s, they can express as R1 equal R on over M here, and R2 equal R on over M. From this equation, it can be seen that the magnitude of the left and right resistance is inversely the proportion to the value of M and N. Thus, when M is larger than N, the R1 is low resistance and R2 is high resistance. So this unit converts the number of on input into resistance. Okay, the bit counting unit is now represented by R1 and R2. Next, I explain the sense amplifier unit. The unit determines the output using the resistance value into two-phase operation, the pre-charge phase and the evaluation phase. In pre-charge phase, when clock signals equal to 0, B1 and B2 are charged to VDD, and then during the evaluation phase, when CLK clock signals equal to 1, the voltage begin to decrease.
Professor Hanyu, sorry, we only have 5 minutes, including the discussion.
Okay. Okay, so I must skip the details. Anyway, this kind of the differential pair circuit and the pre-charge evaluate phase operation is using the bit counting circuit is very simply realized, as shown in these figures. And we must carefully check this details. Okay, this is ideally this kind of operation is successful, as shown in this figure. So we can check the structural operation is done by using these circuit structures. But you can see if we consider the transistor variation is if the transistor varies, the process rule. This is in this case, the process is 49-meter CMOS, and by using the H-spice simulation, if the transistor parameter is varied, then this result is a little bit different. Then we consider these kinds of the compensate unit by using this MTJ. So by the programming this MTJ value, then we can, and this one is a two type of the MTJ. Only the by using only one MTJ, the two pattern program is possible, and we use the three MTJ. There's four pattern, four different transistor levels is realized by using this combination. So you can see we can true operation is successfully done. So we can check. You can see this green bar is this is error. This is the correct value, but this is error. But if you use the three MTJ, this four pattern programming, so we can perfectly realize these kinds of. We can perfectly remove the errors. In this way, our realization is a very simple realization and very robust. We have very strong robustness by using MTJ techniques, compensation techniques. And so we can get the result, very great reduction. The EDP product and the other energy is also great reduction is possible. Okay, so in this way, we just move to the conclusion. So you can see the very potential advantage by using the non-volatile logic memory circuit. And of course, we just collaborate with CMOS circuit techniques and non-volatile logic technique, but many computing. We are now focusing on these kind of stochastic computing and also the quantum computing areas by using the non-volatile logic systems. Okay, so sorry. Okay, that concludes my presentation. Thank you very much for your attention.
Thank you very much, Professor Hanyu. So if you have any question, please raise your hand. No, can I ask a question?
Okay.
Thank you very much. These days, we are using the FPGA, and this is high-performance FPGA becomes really hot, so it's really difficult to cool down the system. And I'm really interesting. And can I ask the operation speed of your non-volatile FPGA?
Okay. So the operation speed is almost compatible with the standard volatile FPGA. Okay. About the MTJ switching speed is at present is also the nanosecond or also the almost compatible. If we use a very high speed FPGA, is a little bit some overhead of the switching speed, but not so high speed application, no problem at present.
Okay, and in your shift registering technique, I thought you use a buffer or something and use a sequential process. So I thought there are some operation speed reduction, but is it correct?
No. Okay.
No.
Yes, this is non-volatile flip-flops is very high speed, almost compatible of the standard flip-flops. So there are no the speed overhead.
Oh, that's nice.
Yeah, so no problem. That's okay.
Thank you very much. And it's almost time. So thank you very much, Professor Hanyu.
Okay, thank you very much.
I'd like to move to the next presentation. The next presentation is by Professor Branjesh Kumar Kaushik from Indian Institute of Technology, Roorkee. Could you prepare your presentation, please? Thank you very much. Maybe your microphone is muted. Oh, thank you.
Am I audible now?
Yeah. We can hear and I can see your slide. So the presentation title is In-Memory Computing Circuit Using Spin Devices. So please start your presentation.
Yeah, I'll just start. So I think the screen and my audio is clear to all of you. I'll just start off with the presentation, and I'll be going through some of the important things related to in-memory computing using all these spin devices. Especially, I'll be focusing more towards this multiple level kind of MTJs. We'll be going ahead with that and trying to see that how these multiple level cells can be used for in-memory computing. So before going to the slides, I'll just speak something about my institute. Now, this institute actually just celebrated its 175th year of inception on 25th November. And this was established in 1847 AD as the first engineering college in the entire British Empire, the Commonwealth nations. So this is, the sprawling campus that you're seeing in front of you. This building is still maintained as it is. It's a sort of a heritage building that we call. Now, moving on to the different areas where we have been focusing, my group has been focusing. We do focus a lot on energy efficient nanoelectronics. Within this ambit, we look into interconnects and different type of interconnects such as copper based or even some 2D material based interconnects. Then also look into optical interconnects, then the different material properties we look into and try to apply for different purposes such as interconnects. We also do research in the area of devices, not only MTJs, but FinFETs, tunnel FETs, so on and so forth. Also, within Spintronics, we do look into devices and memories all based on these Spintronics, especially the multi-level cells and their usage for neuromorphic computing. And within this ambit of interconnects, we do look into 3D kind of integrations, 2.5D and TSVs also. So we normally look into these aspects, but as of now, we have been focusing a lot on spin-based devices, and the areas where we have been working on spin-based spin systems or maybe devices. So this is where actually we have been focusing in Spintronics, where we have done work on memories using single level cells or multi-level cells. This is how it looks like. We'll be discussing more about this multi-level cells in today's talk, and then taking it forward to computing in memory, logic in memory, so on and so forth. We also do focus on skyrmions, domain walls based memories, devices, also look applications of these devices into hardware security, and then also look into the logics based on these Spintronics. So we do come up with full adder, either a standalone full adder or sort of computing in memory based full adders also and compressors. So these are some of the designs which we carry forward, which we take into consideration while working with these MTJs and different cells. Also, we had been looking into quantum computing using these kind of structures, trying to implement sort of gates, then also looking into the adders, and then Fourier transforms, so on and so forth, using these kind of structures. Recently, we have also been working on to application of all these spin-based devices into artificial intelligence-based neuromorphic system, either non-spiking ones and spiking ones, trying to implement those characteristics of better devices onto these kind of systems. And of course, one of the important areas where some of the applications of Spintronics can be looked into is radiation hardened kind of designs. So we do look into these areas also. So as of now, Spintronics do have huge opportunity of working into different domains. And that is how, it has been spreading out into different fields. So these are just few fields which I have been talking about. Of course, we do have a lot of other fields also where people can focus into. But these are some of the areas where we have been focusing. Now, today's talk actually being limited to only 30 minutes, I thought of, going ahead with the, sort of designs that we have done, or, some of the other researchers across the world have been carrying out, especially in memory kind of computing, which has been really, upcoming area. So there have been a lot of talks. I was just going through some of the talks earlier also, and I could see that most of the speakers have introduced in-memory computing. So I'll be just taking that quickly. And also the introduction of Spintronics has been dealt out quite widely and in depth. So I think we can quickly go through that and focus more on in-memory computing kind of architecture. So in-memory computing applications will be actually looking usage of these memories and then coming up with different logics using different cells. And also we'll be taking it forward to sort of neuromorphic computing that we have been doing. So, as of now, introduction of Spintronics has been already done by many people. So I think just to quickly look into, we do have, a lot of issues with current CMOS technology. We are not competing exactly against CMOS, but of course, sort of systems that we require as on date is, having CMOS and spin-based devices all together. That is how we can, go ahead. All spin kind of systems would be still a challenge, because the peripherals and other things have to be supported by CMOS. So, but anyway, when we talk about memories, as on date, with CMOS technology, we have SRAM, DRAM, and all those kind of flash memories, and they have their own limitations. So when we talk about SRAM, they have their own high standby power consumption. When we talk about DRAM, they are also power hungry, and they do have a lot of latency also. Reason being that it requires a lot of refresh current. And apart from this, when we talk about flash memory, which has been covering the entire market as on date with mobile phones and other kind of memories where we have to store BIOS and other things, these flash memories do have a lot of limitations in terms of endurance, maybe just up to 10⁵ cycles for which we can write. And then, they do have very high write power also. So, they are, of course, limited to just few applications. And as on date, we do require some universal memories, that can inherit all the good properties of SRAMs, DRAMs, flash, so on and so forth. And that would be, that would be quite fast, scalable, should have low power, should have, of course, high endurance and, non-volatility, which has been really very promising as on date, keeping in mind the high standby power consumption which SRAMs has. Now, these are some of the good properties that we find out with the Spintronics, which has been explored a lot, over last almost a decade now. And as on date, we do have, commercial MTJs and memories, some of the leading companies such as Everspin, so on and so forth. There are many other companies also who have been actually able to replace DRAMs, by these spin-based memories. And of course, there are a lot of other things which has been carried out across the world. Now, when we look into Spintronics, the basic device that we come across is your MTJ, which can have sort of a parallel state, which is considered to be zero state, logic zero state, and an anti-parallel state, which is, sort of considered as anti-parallel state and having, state of 1. And this is how the resistance can vary as we move from parallel to anti-parallel or anti-parallel to parallel kind of switching with different currents that we apply across it. And of course, the TMR is something which is very important for working with these kind of devices. There are many other parameters, but of course, TMR has been gaining a lot of interest. Reason being that they are considered one of the noise margins to work on with. And of course, they decide how many levels. When we work with multiple levels of cells, they of course decide how many levels we can put up. This resistance has to be something which is very important to be considered. Now, moving on, there are a lot of devices which has been proposed over the years, especially STT, voltage controlled SRAMs, then your SOTs, MRAMs, then your domain wall memories and skyrmions. So huge number of devices have been proposed over the years, and people have been researching a lot. But as far as commercial aspects are concerned, the industries are yet to switch to even SOT MRAMs very well. So they are still working out with STT MRAMs, so on and so forth. Of course, they have their own limitations and other things have to be looked into. These are some of the papers which I am referring is from the group who have been conducting all these workshops. Yeah. So now, when you talk about Spintronic devices, all of these devices do have their merits and demerits. If you start with NAND flash, of course, the write time, read time, and all these parameters when we look into. Your NAND flash had something which was quite miserable in terms of properties, in terms of endurance, your energy per bit, so on and so forth. So as we move on gradually, of course, DRAM has been there for quite a long time, celebrated 50 years of inception in 2020. And SRAM has also been there for a long time, but then you see that, they have been now struggling a lot as far as power is concerned. Now, to take care of all these aspects, when we talk about STT-MRAM, the write time is something like less to 10 nanoseconds. Of course, not better than SRAMs, but sometimes better than your DRAM, most of the times. As far as your energy is concerned, of course, they are almost compatible or comparable to that of your DRAMs and SRAMs. That has improved over the time with different kind of devices that we see across. When we talk about endurance, nothing matches well with your DRAM or SRAMs, but then VCMA and these STT-MRAMs have come up over the years very well, and now they are matching very well with all these kind of devices as of now. So of course, they are having a lot of good properties in terms of non-volatility, wherein the static power dissipation can be taken care of. So these are some of the quick glimpse about how these Spintronic devices have been coming up. Of course, speed is something which is coming up very nicely, and of course, optically switched MTJs is something which is going to do many tricks as far as timing is concerned, but then they have their own issues of fabrication and putting lasers onto the chip also. So those things can be looked into, but as of now, they have huge benefits. And of course, that is coming up with a lot of challenges. So we have been actually focusing, one of the domains of multi-level cell using Spintronic devices, wherein we are trying to see that how the density of all these memories can be increased. So we have been actually exploring two level cells wherein they are either put in series or they are put into cascade. And we had done a lot of analysis also as far as the noise margins are concerned, as far as their temperature variations are concerned, and then whether we are able to read out them clearly and distinguishably or not. So all those things we have been looking into, and as a quick glimpse, you people can look into these work that has been published, and see that how these performance actually get affected. Of course, not only us, but there are a lot of other groups also who have been, looking into multiple stacks of these, memories of MTJs. One of them, being switched by SOTs, and the spin orbit torque, and the other one, using STTs. So all kind of devices have been looked into. And then we also looked into, all voltage controlled spin orbit torque MRAMs, wherein, this heavy metal layer is responsible for switching the free layer on this side and on the down side. And both of these dimensions have been kept apart, so that there is a clear distinguishing factor between the currents that would be required to switch both of these devices. And similarly, this is another design that has been proposed and looked into and seen that how it can work. There are a few other groups also who had looked into these kind of devices, but then we went forward with many other analyses also. Apart from this 2 levels, we also worked on a multi-level cell using Spintronic devices. This is one work which was carried out by another group. Seeing that you have a heavy metal layer on the bottom, then you have one more significant bit, and then intermediate bit, and sort of low significant bit onto this side. And all of these devices are actually written in different steps, and also read through different process. They have, it's not that one step process it would be read out, but need to follow certain steps. And of course, there would be certain delay because of number of steps involved. But the main focus of these kind of devices is to increase the density and harness the area advantages also. Right? So this is another kind of devices which were proposed earlier, where all of those 3 bits were stacked. But of course, this would be having a lot of issues with different resistance levels that we can achieve, and the noise margins that would be available. And coupled with the variations, if you take into consideration, things would get even worse. So this is another variant where we have again, used a SOT mechanism to switch both of these devices together, and keeping the third device switched by STT mechanism. And then taking it forward, went ahead with the different multi-level cell, sort of a 4-bit cells that could be switched. So these are the 2 bits on the 2 sides, and this is 2 opposite bits that could be, extended further. And we saw actually its application for different other purposes also. This is another kind of structure that we proposed, keeping into mind that we can have 4 stacks put together, and the mechanism would be, quite complicated, of course, to write it down, but then you get a benefit in terms of area density. Right? So the 2 devices on the top and bottom would be switched by SOT mechanism, and this is using STT, and of course, somewhere STT plus SOT mechanism also. So we carried out all SPICE related kind of analysis and found that this is workable. And then when we try to make a comparison, performance comparison, of course, you do have a lot of benefits in terms of area, especially. You can see that area for each of these bits, if you take into consideration area per bit, that would be reduced a lot. And when we talk about write latencies, this is something, which is coming out to be quite okay in comparison to a single STT that we see over here. Not better than what we see with SOT, but our focus had been more towards increasing the density and also the energy per bit that would be required. You can see the energy per bit could be reduced enormously in this case. Now, of course, I'll not go into much detail. We do have a lot of benefits in memory computing in comparison to von Neumann architecture that we had earlier. And this is what we tried it out with the different STTs and other kind of devices put into the fabric of this memory, and then try to use it for different purposes. Right? So of course, the peripherals were all based on CMOS. We're not getting rid of these things altogether. We're just changing the fabric and trying to see that how these kind of in-memory computing can be actually taken care of. So this is one actually work which has been carried out by another group to see how the AND operation and OR operation can be done using these kind of fabrics. Of course, I'm not going to the details because that would be taking much of the time to understand actually what are the steps that we need to follow to get into these kind of operations. Now, similarly, we can use the SOT MRAM based IMCs also in memory computing fabric, where we have a 3-terminal kind of device, and this is what has been shown earlier. It was being people considered that it is quite difficult to go ahead with 3-terminal, but it does work a lot. Right? It does work well. And this is a work that was carried out by another group, and they showed, that it does help in terms of energy, in terms of, leakage power and area as well. This is, another work which takes into consideration domain wall motion device based IMC, where, domain wall is used, and the different SOT mechanisms and spin Hall effect mechanism is used to create this device, put into the fabric, and see the functionality of all these kind of system, how it works out. And what we did is, this is something which we carried out. This is more focused towards, again, using these multi-level cells for having different mechanisms done. So we did use, this is 2 levels that we used of MTJs, and these are the 2 bits that we used, and then followed it up with the different steps at different locations. We could have this, these are the 2 inputs, then we could, the next step we could calculate the sum, and then the carry and the output carry based on all these inputs and output. And this is all done using different steps of mechanism. But the best thing about it is that once we have 2 bits put together, the number of steps involved in comparison to your STT would be reduced, and also the area that is required with these kind of fabrics would be reduced. So we went ahead with not only proposing different devices with multiple levels, but also taking it forward for in-memory kind of computing. And this is what we can show that we went with your SOT-M also for creating these kind of CM architecture, and this is where the comparison can be seen for von Neumann and for your CIM architecture. When we compare it with just AND operations, of course the power dissipation is much more reduced over here. And similarly for your OR and NOR operation, and for your XOR and XNOR operation. And that was taken forward for your magnetic full adder, also creating these kind of fabrics. And we can see that they do give a lot of advantage in terms of not only power dissipation, but also the area characteristics as far as the other kind of devices are concerned. I'm not talking about standalone kind of XNOR or XOR, but memory fabric, based other kind of stuff where we have just 1 bit of information stored at one location. So, this is something which we carried forward with the 3-level cells and 2-level cells also. This is again showing a CIM architecture based on multiple level, 2-level cells, and tried to, calculate this NAND, NOR, XNOR operations and some operation over here in this memory fabric. This was again, compared with the other kind of stuff also. Other kind of cells, STT and SOTs. This is a 3-level cell, series 3-level cell where the switching was being done using STT and SOT mechanism. This is where the 3-level cell has been shown. So all these inputs can be taken into consideration, A, B, and the carry which is coming from the previous stage. And then, coming up with their sum operations, NAND and operation, NOR and OR operation. And you can see the peripherals is, of course, based on the CMOS kind of, architectures. And then, once we make a comparison, once we see the comparison of all these kind of, devices based in-memory computing, you can see that, the device counts, if you see in just CMOS full adder based, it is 46 transistors that has to be used over here. Now, when we talk about magnetic full adder using STT, we need 38 transistors plus 4 MTJs, and the power dissipation is almost comparable to that of your CMOS. But of course, the delay and other things can be improved. When we look into the STT SHG mechanism, we do require something like 44 transistors, the transistors and these things. While designing all these fabrics, we tried to keep the power dissipation as low as possible. The designs were made out so that the power dissipation could be reduced. And of course, the delay also we tried to reduce as much as possible by using different mechanisms with different architectures. The proposed TLC, this is something which has been proposed earlier by different people. And now the proposed TLC, which is triple level cell based CIM MFA, what we observe is the power dissipation is something which is really reduced. And the delay is also reduced in comparison to some of the previous designs that were proposed. Now, when we take into consideration different other things also, such as your SHG based CIM, then your VC voltage controlled SHG MLCs, right? And the proposed DSH, that is dual kind of cells that we had. So this is where what we see is the read delay is reduced in comparison. The read delay is not reduced much, but then what we see is the technology nodes, the write delay is something which is reduced, and the write energy is something which is reduced per bit. That is what we can see. And the read delay and other things, they almost remain the same, because of course, that is something which is not of much concern. Of course, people can look into Skyrmion-based logic in memory architecture also. This is one actually paper which I could look into, wherein they have proposed logic in memory using Skyrmions also, right? And they have shown that how the things can be improved in terms of power consumption once we are using this Skyrmion-based logic in memory architecture. And taking forward, these kind of designs of MLCs and this in-memory kind of computings that can be taken forward for neuromorphic computing as well. I do understand that there have been a lot of talks related to AI also in this workshop. So skipping those things and taking it forward quickly, this is something your neuromorphic architecture that can be created with STT neurons. This is something which was proposed in 2015 by Kaushik Roy group. And that actually showed that how these synapses, resistive synapses can be created with different MTJs being used for read and write purposes. And then accordingly, the same fabric could be put out for your CNN, convolutional neural network, using your multi-level STT-MRAM based IMC accelerators. This is again, brought out to a very good domain of putting in-memory computing and neuromorphic computing together. This is something hard to design, but of course, people have come up with these kind of solutions. So we also, went ahead with the all-spin binary neural network using voltage-controlled SOT device, right, wherein we came up with your synaptic XNOR module using series and parallel Nvsot. Right? So these kind of two configurations, we tried it out. One is your series and one is your parallel, and trying to see that how the sigmoid and other activation functions could be realized with these kind of devices. And furthermore, also we went with the all-spin binary neural network using the same voltage controlled SOT devices, wherein the implementation of all spin BNN using an 8-bit synaptic crossbar and 2 output spin neurons were taken into consideration. And this really worked well in terms of different performance parameters. So if we talk the different design parameters of the performance parameters, we tried to compare the number of bits per cell that could be put out. Maybe using this only VSOTM synapse, we could put out only, we could place only 1 bit over there. As we move on with the series Nvsotm synapses, this is something where we could, using parallel and series kind of combinations, we could bring out 2 for each of them. And of course, the number of synaptic cells for 8-bit that would be required is 8 because each of them is having 8, but then this could be reduced to 4 and 4 over here with series and parallel. And if you see furthermore, the best thing is that we were able to reduce the transistors that were being required. And the transistor is something which is going to take, much of the area, the silicon area. So that way, the overall area can be reduced, by reducing the number of transistors. And this is where, we also gain in terms of average power on synaptic array. So this is something quite encouraging, using this series and parallel Nvsotms. And then when we talk about energy dissipation, it gives a clear-cut advantage again, in terms of, this is all in femtojoules that has been calculated. And this is something which is quite encouraging when we go ahead with, multi-level kind of cells. Now, these kind of devices have not only been used for, just for doing some BNNs, but of course, people have taken it forward for image edge detections also, right? Wherein the input binary matrix had been, created using these kind of devices. And then people showed that, of course, using these kind of devices, we could do some edge detections also. This is one group which has been, able to come up with these kind of results. So we also went ahead with your digit recognition using Nvsotm. This is my last slide. Just wanted to make a comparison of all these kind of devices that we had been, using over the time and showing that how the proposed Nvsotm would be better. This is somewhere we had tried to recognize the digits, handwritten digits, and this was observed. And these are some of the steps that through which we had gone through, tried to see that how the performance would be improved using this Nvsotm kind of structure. And it could be clearly observed that, the Nvsotm was, of course, using much lesser area in comparison to your CMOS-based SRAM kind of arrays. And of course, with PCM also, with RRAM also, with, the things were quite improved. But of course, it was almost comparable to VSOTM. And STTM that was anyway smaller in terms of area. When we talk in terms of latency, this is something which is really good in comparison to all other non-volatile kind of stuff that we have, non-volatile kind of devices that we have, but not better than what we have with your CMOS SRAM. When we talk about in terms of energy, this is something which is best in comparison to all other competitors. And leakage power is something again, which is quite healthy and quite better in comparison to other kind of devices that we have. And accuracy, you can see that it's almost comparable with all the devices that we have. So this Nvsotm, of course, was a clear-cut winner in comparison to some of its competitors. So I think we can, of course, take it forward for image detections and other kind of things in future as well. So this is all actually I just wanted to talk about and make you or instill the people to work forward in this and to look forward in this area to look different applications using these multi-level cells. Huge applications are there, probably using these multiple level cells. Of course, there are a lot of challenges, but then it does come with a lot of advantages also.
Thank you very much, Professor Kaushik. So we'd like to move to the discussion part. And Professor Hanyu, please.
Okay, so thank you very much for a very wonderful talk. So could you show me the slide 23?
Okay, I'll just go through.
23, yeah.
23, okay.
Yeah, 23.
Yeah.
Okay, so, okay, you showed the summary comparison results. I wonder this evaluation is fabricated chip or the simulation?
Can you please repeat?
Do you have any real chip?
No, we did not have the real chip. We have done this based on simulations. So as of now, creating all these things on a chip would be really a challenge for us. But we did simulations. Carried out all these.
So do you have any schedule to fabricate these architecture?
Yeah, we are in talk with some of the people who have been fabricating these things, and we look forward for at least going ahead with 2-level cells, not 3-level or 4-level. That would be something which would be quite challenging, putting heavy metal layer in between. But of course, we are looking forward for doing at least 2-level cells in future.
Okay, so and one more question. Usually you must consider the parameter variation effects, because the transistor, the MTJ parameter is variated, fluctuating in the fabrication. So these effects must be considered. Did you consider these things?
Which basic factor you mean, please?
Because device fabrication, the chip fabrication, it must be considered the parameter, transistor parameter variation effects, and the MTJ also the device parameter variation, it happens. So you must consider these kinds of effects.
Yeah, so we actually considered the process variation effects, all the variations of transistors and also of MTJs. So while simulations, we carried out a lot of Monte Carlo simulations, keeping all the variations which are available, that we took into consideration and came up with these results. So as far as simulations are concerned, we do take into consideration all these variations.
Okay, thank you. Anyway, it's in-memory computing is I love these kinds of architecture. So in the future, we'd have to collaborate with you. Thank you very much.
Yeah, thank you. Nice to have your comments about it.
Thank you, Hanyu Sensei. And any other guys, do you have any questions? No. Then it's almost time. So thank you very much for a very interesting talk, Professor Kaushik. And I think the multi-layer MTJ is very nice for doing a logic operation. So I'm looking forward to see actual device.
Yeah,
thank you very much.
Me too. Thank you.
So I'd like to move to the next presentation. This is the final presentation in this morning, and the presentation is from by Professor Sato from Tohoku University, and the title is Spiking Neural Network Hardware for Reasonable Computing. So please start the presentation.
Can you see the slides?
Yes, sorry, my microphone is muted.
Okay.
Yes.
Okay. Thank you for the introduction. I'm Shigeo Sato from Tohoku University. Sorry. First of all, I would like to thank the organizers for giving me this nice opportunity. Today, I will talk on this spiking neural network hardware, and these are collaborators. And this work has been done mainly by Dr. Moria and Mr. Tamura. Okay. And this is the contents of my talk. Recently, we have started a research project on Spintronics-based edge computing hardware. In this talk, I'd like to briefly introduce the project and then talk on analog CMOS neuron circuits. Actually, we study two types of neuron circuits. And then let me explain about the application of such circuits to reservoir computing. And also, I'd like to explain about our learning circuit. Finally, I summarize my talk. So this is a background of our research. As mentioned in the previous talks in this seminar, now edge computing is necessary for several reasons. Computing at the edges is essential for real-time processing and reduction of traffic and keeping privacy and so on. So now artificial intelligence processing is moving from cloud to edge. This graph shows prediction of attach rates of AI edge device. Various applications various applications require AI processing. The rates will rapidly increase in next 5 years. Higher rates found for smart speaker, automotive, mobile phones, and PC and tablets. So this is a reason why efficient AI hardware is required. So let us see the performance of AI hardware at present. This data is taken from the website of Tsinghua University, China. The horizontal axis is power, watt. The vertical axis is giga operations per second. Various hardware are given as points. It can be seen that 100 TOPS per watt, T means tera, TOPS per watt is achieved with ASICs here. Further improvement is required for social implementation of AI, we think. 1,000 TOPS per watt is our present target here. To operate edge devices with harvested energy. We suppose that 1 milliwatt is given as harvested energy and 1 TOPS is required for simple recognition tasks, like face recognition. So for edge computing, reduction of electrical power is one of the most important issues. A simple solution to reduce power is use of non-volatile memories. Recently, many non-volatile memories have been developed. These figures show some examples of such memories and their applications to neural networks. First one is phase change memory by IBM. It is applied to Hopfield network. And second one is ferroelectric memory by Panasonic. And Memory Star by UCSB. And last one is Spintronics Devices. This is our result. We collaborate with Professor Fukami and Professor Horio. At present, many kinds of memories have been studied. Spintronics devices have many advantages. As mentioned in the previous talk, I think especially a superior endurance property is quite useful. We can update memory values again and again, no degradation occurs. So it is suitable for learning for neural network. So this slide shows Spintronic devices, a device developed by Professor Ono and Professor Fukami. I do not go into details, but we use this device as a kind of memory star. This is a I and resistance, current and resistance relation. In order to confirm the feasibility of this device in application to a neural network, we developed an artificial neural network composed of FPGA and Spintronics devices. Yeah, this is a collaboration with Professor Ono and Fukami Laboratory. we have SOT device and multiplexer, demultiplexer, and the FPGA board. Okay. So to demonstrate the proof of concept, we choose an associative memory operation because it is simple operation, but is one of typical neural information processing. The system is designed to associate these memory patterns from noisy input patterns. The important point is that the SOT devices are served as synapses, where its analog nature is fully utilized. We realize a popular network with 9 neurons and 36 synapses because popular network has symmetrical connections. These memory patterns are shown. These memory patterns are memorized in the system. I, C, T. We use the synaptic weights obtained according to the theory, but found the performance is not so good. This is caused by device fluctuations. The performance was evaluated this direction sign, which indicates the similarity between memorized pattern and retrieved pattern. So then we perform additional learning like Boltzmann massing, Hebbian and anti-Hebbian learning. So the performance improved. So anyway, we could successfully confirm the pattern association ability of this system. So from such a background, our research project has started 2 years ago. The title of the project is Spintronics-based edge computing hardware fundamentals. The research period is 5 years and a half. Our core members are me, Sato, and Professor Hanyu is the first speaker in this session, and Professor Fukami. Professor Fukami spoke yesterday. We study 3 types of hardware: digital, analog, and stochastic. Digital circuit is suitable for implementing large-scale network, so it can be applied to deep learning. BC binary connection neural network has been studied by Professor Hanyu, as explained in his talk. Analog circuit is has good efficiency and is suitable for realizing complex dynamics. So it can be applied to reservoir computing. Finally, stochastic operation is suitable for annealing. We think combinatorial optimization problems should be solved at edges. We integrated 3 hardware for edge AI in this project. So here, I'd like to move a specific topic. Our group studies analog circuit, CMOS analog circuit. To utilize the advantage of non-volatile analog memory, compatible analog circuit is necessary. We study an analogous circuit of the EGKPG neuron mode. We pay much attention to this EGKPG neuron model because it reproduces various spikes with less calculation cost. These are reports about analog neural circuits, representative ones, University of Manchester, Qualcomm, University of Tokyo, University of Zurich. Generally speaking, about 10 to 40 transistors are required for a single neuron circuit. Of course, operation in the weak inversion region leads to low power consumption. However, we did not much experience in designing such a circuit operating in substation region, so that we considered circuit operation in the strong inversion region as the first step. In this talk, first we propose improved analog MOS circuit of EGKPG neuron model and show some experimental results. Then for further reduction of power consumption, I would like to show another design of neuron circuit which operates in the subthreshold region. I will talk on two types of neuron circuits. Before I show the result related to circuits, I explain a bit about this HKBG neuron model. It reproduces various spikes as shown here, regular spike, ideologically bursting, and so on. While the calculation cost is very low, such a simple dynamics is suitable for not only for brain simulation, but also for circuit implementation. The dynamics is described by these three equations. There are two variables, B and U. B represents membrane potential, and U represents the membrane recovery variable. Prime denotes the time derivative. If we exceed some threshold, both B and U are reset. The right figure shows neuroclines of B and U. And the arrows indicate velocity in BU plane. It can be seen that the equation 1 is expressed in quadratic form. So it is easily realized with most transistors operating in the strong inversion region. As a starting point, we consider the previous work by University of Manchester. The circuit is composed of three parts according to the equations in the previous slides. B-related circuit and the U-related circuit and the comparator. B and U are expressed as a voltages here and here. The comparator generates reset signals here and here. The block diagram of the circuit is shown here. If the current is sufficiently large, V rapidly increases and the circuit output spikes. At the same time, the comparator resets both B and U. We think the circuit is well optimized, but there are some discrepancies between the circuit and the original HKBG neuron model. The dynamics related to B is different from the original model. The reset operation of U is different. U is reset to FD, not U plus D. Okay. And the circuit operates with 3.3 volt voltage source because they proposed the circuit in 2008. But now the source voltage of advanced LSI is reduced to 1.0 volt. So that's a problem. We fixed these issues, not totally, but partially. This is the improved B circuit. The current charge is the capacitor CV, and the M2 generates V squared current in the this corresponds to the first term in the right-hand side. Also, M4 and M6 correspond to the second and fourth terms, respectively. This is an actual equation of the circuit, a bit complicated. This is a improved U circuit. This differential pair generates a term P minus epsilon U. Epsilon is close to 2. This part is dedicated to reset the voltage U here. U is set to U plus U G BD. G is a kind of nonlinear function of BD. Okay, let us compare the original circuit and the proposed circuit. These neuroclines and velocity vectors are shown. We assume 1.0 volt voltage source, which is also applied to the original circuit proposed by University of Manchester. It is obtained by SPICE simulation. It can be seen that the SPICE circuit dynamics in the proposed circuit becomes closer to that of original model. Parabolic property of the nuclein V is successfully obtained, while the saturation property of nuclein of U is found here and here. This is due to the low voltage operation, low voltage supply. But the simulations show that the effect of this non-linearity is negligibly small. So probably the circuit works well. So I would like to show some simulation result. It is obtained by SPICE simulation. The time change of the membrane potential B is given in the left figure. The circuit outputs regular spikes. In regular spiking, spike intervals increases with time. This is referred as adaptation, which is found in biological brains. The right figure shows the state change in BU plane, blue cup, like this. The circuit operates as we expected. Also, we confirmed other types of spikes, fast spiking, shattering, and intrinsically bursting. Bias parameters are shown in the right figure, VC and PT. Actually, the original circuit proposed by University of Manchester can work with 1.0 volt voltage supply. So we check the phase diagram. In comparison with the original circuit, the parameter range of CH and IB are enlarged. We have fabricated the proposed circuit using TSMC 65 nanometer CMOS technology. The chip size is 2 by 2 millimeter square. Supply voltage is 1.0. This is a layout pattern of a single new circuit. Capacitors here and here occupy a large area. This is because we intended to exclude the effect of parasitic capacitances. So we can make these capacitors make it smaller in future. These are the measurement result. The horizontal axis is time and vertical axis is B. Though the dynamic range, so B is small, narrow. Various spikes have been reproduced. This narrow dynamic range is caused by the low drivability of output buffer. We made some output buffers to measure the B, but the drivability of such buffer is quite low. So, but however, the circuit itself works as expected. Okay, this is a comparison with previous studies. Our circuit is here. The proposed circuit show improved controllability, while the power consumption is almost the same with the circuit proposed by University of Manchester. Our circuit is 18 microwatt. This is compatible. By using the weak inversion relation, the power consumption of the execution neuron model, execution model neuron circuit can be reduced greatly. Okay. Okay, so let us see the effect of substrate operation. Maybe you know this kind of behavior, but let me introduce briefly. This is an elementary voltage current relation of an NMOS transistor. Here we have a single NMOS transistor. The horizontal axis is gate voltage. The vertical axis is current. In the strong inversion, the current increases as a linear or quadratic function of the gate voltage. On the contrary, the current exponentially increases in the weak inversion region. The current is several orders of magnitude smaller than that of the strong inversion region. Okay, so therefore we redesigned the circuit working with a low voltage source. The voltage of supply is 0.3 volt. The circuit is composed of 19 transistors. All transistors operate in the saturation region because the supply voltage is 0.3 volt. So we add the two inverters. I do not go into this, but concept is the same. We add some two inverters here for amplify the reset signal from the comparator for stable operation. The circuit successfully operates like the distribution neuron model. Okay, I would like to show some simulation result. This result indicates that various spikes reproduced. Again, regular spiking, fast spiking, shuttering, and intrinsically bursting. In fast spiking, spike intervals does not change, unlike regular spiking. In chattering and intrinsically bursting, dynamical behavior depending on two time constants has confirmed. Fast frequency, high frequency, and low frequency. Okay. Now let us see the dynamical behavior in the BU plane. Each arrow represents velocity, and orange and green curves correspond to null lines of B and U. B and U. Blue curves indicate the state change like this. So it seems that null lines are different from the original model, but similar dynamics is obtained. Anyway, so one of the promising applications of such a recurrent neural network is reservoir computing. It is possible to recognize spatial temporal input signals utilizing higher dimensional mapping function of reservoir neurons. Here, it is composed of three parts: input reservoir and readout layers. Okay. So as an example, we consider a neural network composed of 10 neurons, shown in the middle. We employ 8, shown in red, 8 excitatory neurons and 2 inhibitory neurons. By choosing proper bias parameters, the neuron can operate either as excitatory neuron or as inhibitory neuron. In this case, an excitatory neuron outputs regular pulses, regular spikes, while an inhibitory neuron outputs fast pulses. The right figure shows the simulation result. Even input signals, the neurons show specific responses. The network can work as a reservoir. Here, let me show the power consumption. Depending on pulse types, power consumption changes. But generally speaking, 10 nanowatt, less than 10 nanowatt is required for a single neuron using the weak inversion region. In addition, the network composed of 10 neurons require less than 8 nanowatt. I think this is small enough, even for edge computing. Low power operation is easily obtained in analog implementation. So this is the comparison with previous studies again. We have 2 circuits here. Now we are measuring the circuit view, the last one. And I'm sorry that I will not show the experimental result today because we're writing a paper. So, but it works as expected. I would like to report the result at another opportunity. The final topic I would like to talk on today is learning. In reservoir computing, the synaptic weights W between reservoir and readout layer must be calculated. Normally, regression is used, which requires extra algebraic calculation. To avoid such extra processing, we would like to use STDP. STDP is the abbreviation of spike timing dependent plasticity. STDP is a learning process found in biological brain. Synaptic weights change depending on relative timing of neurons' output and input action potentials. For example, if a pre-neuron fires firstly and then post-neuron follows, the synaptic weight here increases. The relation between weight change, synaptic change, and the time difference is given in the right figure. This is a typical STDP curve. And in some cases, an STDP having decay property shows better performance. We have confirmed such a property by simulations. Decay process corresponds to synaptic pruning. An STDP curve with decay property is shown red in this figure. And these figures illustrate spike timing, pre and post neurons, spike timings, and weight changes. The last parts, lower parts, without decay and with decay. So we design an STDP circuit using analog CMOS circuit. I do not go into details, but it is composed of 4 units. The center unit converts time difference to voltage. The voltage of the capacitor CW corresponds to the weight change. The unit colored red is decay unit. So we check the circuit behavior by simulation using TSMC 65 nanometer CMOS technology. Most STDP curves with and without decay are successfully obtained with the proposed circuit. Most of transistors operate in the subthreshold region to minimize power consumption. The implementation of the circuit remains as a future work. Okay. So let me summarize my talk. We proposed an improved EZQBit neuron circuit and fabricated it using 65 nanometer CMOS technology. We designed another neuron circuit which operates in the weak inversion region. Numerical simulation shows that the power consumption can be reduced to less than 10 nanowatt for a single neuron. It is very low. STDP curve having decay property has been obtained with some neuron circuit. But design only. We have to check this behavior by making a circuit, making IC. Low power reservoir computing using analog neuron circuit is expected for edge computing. Okay, that's all. Thank you for your attention.
Thank you very much, Professor Sato. And now let's move to the discussion part. So if you have a question, please raise your hand in the Zoom. No one have. Can I ask a question?
Yes.
Could you show slide number 28?
28.
About neural reservoir computing.
This one?
No, next slide. Yeah, thank you very much. Yeah, this one. Is this number 5 node is a special one because it's connect on, this node is only connects vice versa to the 2 and 5.
Mm-hmm.
So, and the results show no response. So this number 5 node is very important because of this 2 to 5 connection.
Oh, yes. We know, but the reason we don't know the exact reason.
Oh, really?
Probably we if we change a parameter, then number 5 reacts. I don't know. It depends on the situation, bias voltage. So
Okay, thank you.
And in this case, it works. It's not so serious problem.
And I think the Elizabeth computing use a random connection weight.
Yes.
So in this case, you choose a parameter of the neuron by using some voltage or something.
Yeah.
And you create lots of different connection and do Elizabeth computing. Am I correct?
In this case, we use a fixed connection.
Fixed. Yeah. But the parameter or the strength of the connection should be random, invisible. And how did you do that?
In this case, we use fixed, not analog, digital connections. But in future, we use analog connections. And in this case, we use transistors. Transistors. And we control the gate voltage of such transistors.
Okay, so the connection strength is different from the other one.
Yeah.
Okay, thank you very much.
And to memorize the synaptic value, we use non-volatile Spintronics memories.
That's nice. So we don't have to apply a constant current to memorize the data. That's very nice.
But it's not so easy.
Yeah. So anyone have question? No? Professor Sato, you already create a neuron by using a subthreshold level CMOS, so you already show a very, very small energy consumption device. So, but you have maybe 3 or 4 years for your CREST project.
Yeah.
Well, could you tell me, if possible, could you show us some future device?
Future device
that you want to create, if possible.
From the viewpoint of applications, we have to make 100 to 1,000 neurons network. So it is not easy, but we are trying to. And probably 100 network is not so difficult. But 1,000 network is not so easy because analog circuit has some, the noise tolerance is not so high in analog implementation. So that's our subject. So, but we hope to make.
So increasing the number of the neuron and implement to the edge device.
Probably.
That's very nice.
But it is not possible to mix the CMOS circuit and Spintronic device mixed together at present. We don't have such process. Yeah.
Okay.
We make such a circuit and device separately and connect. After this project, maybe someone make mixed circuit, mixed device. Okay.
So
Professor Kami tried to develop such analog memories, but it requires maybe 3, 4 years after. I don't know.
But maybe the device is very nice in-memory neuron.
Yeah.
Okay, thank you very much. I have questions. No. Okay, then I'd like to close this session. So thank you very much, Professor Sato, for an interesting talk. And thanks everyone for discussion. So do you have any announcement from the office?
Thank you for sharing. Thanks all the speakers and thank the audience for attending. Let's meet again after 4 hours. So Singapore time 3 p.m. and Japan time 4 p.m. See you all.
See you in the afternoon. Thank you.
Thank you.
Bye.